Algebra by Michael Artin. Chapter 2, Groups. Section 3, Isomorphisms. Section 3, Isomorphisms. Let G and G' be two groups. We want to say that they are isomorphic if all properties of the group structure of G hold for G' as well, and conversely. For example, let G be the set of real matrices of the form 1, x, 0, 1. This is a subgroup of GL2R, and the product of two such matrices is 1x01 times 1y01 equals 1x plus y01. The upper right entries of the matrix add when the matrices are multiplied, the rest of the matrix being fixed. So when computing with such matrices, we need to keep track of only the upper right entry. This fact is expressed formally by saying that the group G is isomorphic to the additive group of real numbers. How to make the concept of isomorphism precise will not be immediately clear, but it turns out that the right way is to relate two groups by a bijective correspondence between their elements, compatible with the laws of composition. That is, a correspondence, 3.1, G to G', having this property. If A and B, members of G, correspond to A' and B', members of G', then the product AB in G corresponds to the product A', B' in G'. When this happens, all properties of the group structure carry over from one group to the other. For example, the identity elements in isomorphic groups G and G' correspond. To see this, say that the identity element 1 of G corresponds to an element epsilon prime in G'. Let A' be an arbitrary element of G', and let A be the corresponding element of G. By assumption, products correspond to products. Since 1A equals A in G, it follows that epsilon prime A' equal A' in G'. In this way, one shows that epsilon prime is equal to 1 prime. Another example, the orders of corresponding elements are equal. If A corresponds to A' in G', then since the correspondence is compatible with multiplication, A to the R power equals 1 if and only if A' to the R power equals 1 prime. Since two isomorphic groups have the same properties, it is often convenient to identify them with each other when speaking informally. For example, the symmetric group Sn of permutations of the set 1 through n is isomorphic to the group of permutation matrices, a subgroup of GLNR, and we often blur the distinction between these two groups. We usually write the correspondence, 3.1, asymmetrically as a function or map from G to G'. Thus, an isomorphism phi from G to G' is a bijective map which is compatible with the laws of composition. If we write out what this compatibility means using function notation for phi, we get the condition 3.2 phi of AB equals phi of A times phi of B for all A and B a member of G. The left side of this equality means to multiply A and B in G and then apply phi, while on the right side the elements phi of A and phi of B, which we denoted by A' and B' before, are multiplied in G'. We could also write this condition as the quantity AB' is equal to A' B'. Of course, the choice of G as domain for this isomorphism is arbitrary. The inverse function, phi inverse mapping G' to G, would serve as well. Two groups G and G' are called isomorphic if there exists an isomorphism phi from G to G'. We will sometimes indicate that two groups are isomorphic by the symbol wavy equal. 3.3. G isomorphic to G' means G is isomorphic to G'. For example, let C equal the set ... comma a to the negative 2 power, comma a to the negative 1, comma 1, comma a squared, comma ... be an infinite cyclic group. Then the map phi mapping Z plus to C, defined by phi of n equal a to the n power, is an isomorphism. Since the notation is additive in the domain and multiplicative in the range, condition 3.2 translates in this case to phi of m plus n equals phi of m times phi of n. or a to the m plus n power equals a to the m times a to the n. One more simple example. Let G equal the set 1, x squared, x to the n minus 1, and G prime equal the set 1, y squared, y to the n minus 1 be two cyclic groups generated by elements x and y of the same order. Then the map which sends x to the I power to y to the I power is an isomorphism. Two cyclic groups of the same order are isomorphic. Recapitulating, two groups G and G prime are isomorphic if there exists an isomorphism phi mapping G to G prime, a bijective map compatible with the laws of composition. The groups isomorphic to a given group G form what is called the isomorphism class of G, and any two groups in an isomorphism class are isomorphic. When one speaks of classifying groups, what is meant is to describe the isomorphism classes. This is too hard to do for all groups, but we will see later that there is, for example, one isomorphism class of groups of order 3, see section 6.13, and that there are two classes of groups of order 4 and 5 classes of groups of order 12, chapter 6, section 5.1. A confusing point about isomorphisms is that there exist isomorphisms from a group G to itself, phi mapping G to G. Such an isomorphism is called an automorphism of G. The identity map is an automorphism, of course, but there are nearly always other automorphisms as well. For example, let G equal the set 1, x squared be a cyclic group of order 3, so that x cubed equal 1. The transposition which interchanges x and x squared is an automorphism of G. 1 maps to 1, x maps to x squared maps to x. This is because x squared is another element of order 3 in the group. If we call this element y, the cyclic subgroup, the set 1, y squared generated by y is the whole group G, because y squared equals x. The automorphism compares the two realizations of G as a cyclic group. The most important example of automorphism is conjugation. Let B, a member of G, be a fixed element. Then conjugation by B is the map phi from G to itself defined by 3.4. Phi of x is equal to B times x times B inverse. This is an automorphism because, first of all, it is compatible with multiplication in the group. Phi of xy equal B times x times y times B inverse equal B times x times B inverse times B times y times B inverse equals phi of x times phi of y. And secondly, it is a bijective map since it has an inverse function, namely conjugation by B inverse. If the group is abelian, then conjugation is the identity map. B inverse equals A B inverse equals A. But any non-commutative group has some non-trivial conjugations, and so it has non-trivial automorphisms. The element B inverse is called the conjugate of A by B and will appear often. Two elements A prime of a group G are called conjugate if A prime is equal to B inverse for some B a member of G. The conjugate behaves in much the same way as the element A itself. For example, it has the same order in the group. This follows from the fact that it is the image of A by an automorphism. The conjugate has a useful though trivial interpretation. Namely, if we denote B inverse by A prime, then 3.5, BA equals A prime B. So we can think of conjugation by B as the change in A which results when one moves B from one side to the other. Algebra by Michael Artin, MIT. This book was published in 1991 by Prentice Hall. It is read by Jim Renholt with programming and illustration by Jim Renholt, 2019. Thank you for listening.